All right, so for 10b, we're going to focus on attributes of exponential functions. So this is actually going to tie in a lot to geometric sequences that we actually just did. So just to kind of refresh your memory, we're going to look at some sequences. So looking at the pattern here, we have 6, 10, 14, and 18. So we are going from 6 to 10 to 14, which is going to be plus 4, and plus 4. So if I want to find the next few terms, I'm just going to continue the pattern. So 18 plus 4 is going to give you 22. 22 plus 4 is going to give you 26. And then 26 plus 4 is going to give you 30. All right, so because we are adding means we are going to be looking at an arithmetic sequence. In an arithmetic sequence, that means we have a common difference. And a common difference implies we're going to have a d value equal to that change, which is 4. So now we want to write the recursive and the explicit forms for the sequence. So the recursive form is going to be a of n equals a of n minus 1 plus that common difference, which is 4. And then your explicit form is going to be the first term, so 6 plus n minus 1 times your common difference, which is 4. So that's for the first sequence that we have here. And now we're going to jump over to the next sequence. All right, so now we're going over here from 2 to 6 to 18 to 54. So this is going to be multiplying by something. You can't add consistently. So to go from 2 to 6, we're multiplying by 3. So 6 times 3, which gives you 18, 18 times 3, which gives you 54. So now if I do 54 times 3, that is 162. Heck yeah. And 62. Then we're going to multiply it by 3 again, which gives you 486. Then multiply that by 3, which gives you 1,458. All right, so there's the first 3 terms, or the next 3 terms of that sequence. And because we're multiplying, that is geometric, which means if it's geometric, that implies we're going to have a common ratio. And that common ratio is going to be equal to 3. All right, and then for your recursive form here, we have a of n equals a of n minus 1 times 3 times your common ratio. And then for your explicit form, it's going to be a of 1. So your first term, which is 2, then times your common ratio, which is 3, then raised to the n minus 1. So that is your explicit form equation. So now we're going to kind of jump into the exponential functions itself. So the exponential functions are going to mirror a lot of a geometric sequence. So we're going to kind of dive in deeper to a geometric sequence for our exponential functions. So just some very important background information on exponential functions. So there are 2 different types. So 2 very distinct types. We have what we call an exponential growth and an exponential decay. So literally kind of think about what those 2 different words mean. So a growth means it's going to be getting bigger, whereas a decay kind of means it's going to be withering away, kind of getting smaller. So an exponential growth, let's do this. So a growth is going to be getting bigger, so it's going to approach positive or negative infinity. Whereas a decay, it's getting smaller, is going to get closer and closer to 0 since it's slowly withering away to nothing. All right. So now we have another vocab term that's very important. So it's called an asymptote. So an asymptote is a line or curve that, or it's a line that never touches a curve, but it gets closer and closer to it. So your asymptote here is going to be a very crucial idea to know. So I kind of give you an example here. So we have 0.1, 0.01, 0.001, 0.0001. It's getting closer and closer to 0, but it never actually equals 0. So that's what an asymptote kind of leans into. So this is actually an idea in calculus called limits. So this kind of, I included that part on purpose specifically to kind of give you guys the idea that even upper level math such as calculus, it's still algebra based. This stuff is never going away. It's going to haunt you forever. I know it haunts me forever. All right, so kind of getting into an exponential growth and decay. So each one of these graphs has two distinct curves. So we have a curve in purple that's going up, and we have a curve in green that's going down. So notice how the equation up here in purple, this is going towards positive infinity. It's never going to stop going up. Whereas the graph down here in green, it's going to continuously forever and ever go down towards negative infinity. All right, so we're going to be kind of looking at both of these graphs side by side, just kind of comparing them. So we want to look at some similarities, some differences. We're going to compare, contrast, and we're going to kind of look to see what all is the same, what's different, how is it different. All right, so for purple, which is our equation going up, so when I say approaches, that's getting closer and closer to positive infinity. All right, and then the domain, we're looking at how far left and right it goes. Well, so far as the domain goes, it's going to be going left and right indefinitely. So that means your domain is all real numbers. Now your range is how far up and down it goes. So right here, let's pick a color. Let's do this color, it'll be yellow. So your asymptote, it's going to get closer and closer to the x-axis, but it's never actually going to equal the x-axis. So even though it looks to be touching that x-axis right here, it's actually not. It's just getting closer and closer and closer and closer. So really similar to this idea up here. Even though it looks like it's zero, it's not zero. It's closer and closer to it. So the idea of these values right here, this is really what's happening. It's getting closer and closer and closer and closer and closer and closer, but it never actually equals zero. All right, so your range, it's only everything above the x-axis. So what that means is your range is all y values, all the y values bigger than zero. So keep in mind, it is not equal to zero. It is not. It is only everything strictly greater than zero. You cannot be equal to zero. That defeats the purpose of an asymptote. So speaking of asymptote, your asymptote itself is the x-axis. So that equation is just y equals zero. So the reason it's y equals zero is if you kind of remember the throwback to Hoibucks. So we have a horizontal line in yellow up here, that dashed line, which means it is a y equals equation. And that y equals equation is at zero. So that is your asymptote. All right, so now we're going to move on to the equation in green. So it's going to get closer and closer to a value. So it's going to approach negative infinity. It's going to get closer and closer downwards. All right, so the domain, similar to before, all real numbers. Wow, that's terrible. That's still terrible. Close enough. All right, your range, in this case, now instead of it being above the x-axis, now it's actually below the x-axis. So in this case, your range is going to be y less than zero. So once again, it's not less than or equal to, it's just strictly less than. Now your asymptote is still going to remain the same. It's still y equals zero. It's getting closer and closer to zero, but it doesn't actually equal zero. All right, so these are your exponential growths. So now we're going to look at the exponential decays. So the decays are going to get closer and closer to zero. So just like before, I'm going to go ahead and draw my little asymptote right here because it's getting closer and closer to zero, but it doesn't actually equal zero. So now up here, so it's going to get closer and closer to zero in the blue, but now for orange, it's still going to get closer and closer to zero. So for the decays, they're actually both approaching the same thing. So when I say approach, we're looking at what we call the end behavior. So the end behavior is like as the graph goes further and further to the right, what's happening to the y value? So as the x value is increasing, the y value is decreasing. It's getting closer and closer to 0. All right, so we're going to kind of look at each of these equations individually. So in blue, it's approaching 0, which makes it a decay. The domain is still all real numbers, just like before. Your range, it's above the x-axis, so it's everything greater than 0. And then your asymptote is still y equals 0. All right, so now on the flip side, now if I do the exponential equation in orange, it's still approaching 0. So it's still a decay here. The domain is still all real numbers. The range, in this case, now because it's below the x-axis, now we want y less than 0. All right. And then your asymptote here, once again, is still the x-axis, which is y equals 0. So I highly recommend just going through all 4 of these different types, look at the graphs, really internalize what's happening. So notice if you look at the very first row of each one of these, you have to look to see what it approaches. What it approaches is going to tell you if it's going to be a growth or a decay. Because I'm not always going to give you the graph. Sometimes I may give you the table. Sometimes I may give you a sequence. Sometimes I may give you an equation. You have to look to see what it's approaching in order to determine if it's a growth or a decay. So if it's approaching infinity or negative infinity, the numbers are getting bigger, it is a growth. If the numbers are getting smaller on the y side, then it is a decay. All right, so the domain across the board is all the same. The range is going to vary and depend on whether the equation is above or below the x-axis. If it's above, it's going to be greater. If it's below, then it's less than. And then for our sake, for the asymptote here, our asymptote is going to continuously be the x-axis, so y equals 0. Just know that if I were to do a vertical transformation, then the asymptote would also change as well. But for our case right now, our asymptote is just going to stay as y equals 0. All right, so moving on. So we're looking at the exponential function equation. So it's very similar to a geometric sequence setup, or at least the explicit form. So just for a frame of reference, right below it, I'm going to write the explicit form for a geometric sequence, just so you guys can kind of see how they're the same and how they're different. So your first term is the first value. And then your common ratio is your b value. So they're very similar. All right, so your a value is your initial amount, or the first term, but it's also your y-intercept, whereas your b value is your common ratio, which is your growth rate. All right, so your growth rate is very important here. So your b value is really the most important component of the entire equation. So your b value is also going to tell you if it's a growth or a decay. So if your b value is bigger than 1, then it is a growth. That should be bigger than 1, not 0. That's a highlighter. It's bigger than 1, that is a growth. All right. However, if it is less than 1 but greater than 0, that is going to tell you it's a decay. All right, so given either the equation, the graph, or the table, you have to determine whether this is going to represent an exponential growth or an exponential decay. So remember, if I give you an equation, you have to look at the value inside the parentheses. If it's bigger than 1, then that's going to tell you it is a growth. If the number inside the parentheses is less than 1, that is going to be a decay. But remember, we're looking at the number inside the parentheses. So 3/2 here, well, that's still bigger than 1, which means this is still a growth. All right, so now looking at number 3 over here, now if I flip it, I'm only looking at 2/3 here. So because it's 2/3, it's less than 1, that is a decay. All right, and number 4 here, we have a growth rate of 0.2. 0.2 is still less than 1, which means we have a decay. All right, so now we're going to look at these equations. So we have to look at what we call the end behavior. So I want to look to see what is it approaching. So as I get further and further here and closer, I'm getting closer and closer to the x-axis here, which means it's approaching 0. So because it's approaching 0, that means we have a decay. Now looking at the next graph here, if you follow the path, the trajectory of it, it's actually getting bigger, but in the negative direction. So it's approaching negative infinity. So what that means, there we go. So what that means is even though it's going in the negative direction, it's actually still a growth. So that's kind of the biggest misconception I see here happening is whenever the graph is going down, people think because it's getting bigger but in a negative direction that it's actually a decay, but it's actually a growth. All right, so now I give you tables. So you kind of have to look at the y values and you have to determine whether it's going to be a growth or a decay based on the y values. So if you look here, notice how the numbers are getting bigger. So because the numbers are getting bigger, what that means is this is a growth. Conversely, over here, as you keep going down the table, the numbers are actually getting smaller and smaller and smaller and smaller. So because the numbers are getting smaller, that implies we have a decay. So half the battle in this lesson is really just identifying if it's a growth or decay. Okay, so now we have to find the following attributes. So you have to be kind of careful on these. So I could give you really any range of these 3 questions here. I can give you the graph, I can give you the equation, or I can give you a table, any one of those. All right, so start with the graph. So we want to determine first if it's a growth or a decay. So just kind of looking at the end behavior, our graph here is, that's terrible. Our graph here is getting closer and closer to positive infinity. That is terrible. To positive infinity. So because it's getting closer and closer to positive infinity, that implies that this equation here is going to be a growth. All right, now your initial value. Remember, your initial value is literally just the y-intercept. All right, so you're looking to see where does it cross the y-axis. All right, so here at this coordinate here, we're going to have 0, 3. So 3 is going to be your initial value. All right, and then our common ratio is going to be the b value. Now for the common ratio, we must find another point. All right, so we have to find the multiplier. So I'm going to look for a point. I'm going to look for either -1 comma something, or you're going to look for 1 comma something. It doesn't matter which one, look for one of them. All right, but if I go over here to 1 comma something, this is going to be 1, 6. All right, so in order to find the common ratio, we're looking at a multiplier. So we're looking to see how do I go from 3 to 6? What do I multiply by to go from 3 to 6? Well, I'm going to multiply by 3 in order to get 6, which means my ratio here is 3. So remember, your ratio is also your b value. All right, so my b value down here is 3. I can't do math, that's 2. Math is really hard, apparently. It's like, hold on, that doesn't look right. Times 2, it's fine. I'm just a math teacher. I don't know math. Everything is fine. There we go. Crisis averted, somewhat. Okay. So now we actually are going to write the equation using the initial value and the common ratio. So our equation, remember, is in the form y equals a parentheses b raised to the x. We're just taking the initial value and the common ratio, plugging it into the corresponding slots. There's your equation. So your equation, you're going to have y equals your a value, which is 3, in parentheses 2 raised to the x. There's your equation. So for this next part, now you actually want to find f of 3. You want to find that specific value. So what that means is I'm going to plug in 3 for my x value. So now keep in mind, your answer here could be a really big number, it could be an okay number, it could be a really small decimal, whatever it is, it's fine. Okay. So 2 to the third power is 8, 8 times 3, which is 24. And you can plug this in the calculator, just plug it in literally how it appears. So 3 parentheses, 2 parentheses, caret 3. So just for a frame of reference, I'll go ahead and just show you just in case. So run matrix. So I'm plugging in 3 parentheses, 2 parentheses, caret, then 3 to find f of 3, which is 24. So you can literally just plug it in the calculator exactly how it appears. If you're someone like me who has to double check 2 plus 2 in the calculator, you go for it. No judgment. It's like, I know 2 plus 2, but just in case math changed, I got to check. All right, your domain, you're looking to see how far left and right it goes. So your domain, as always, is all real numbers. This should be your freebie on any assessment. I cannot draw the symbol to save my life. Hello. There we go. No. It's okay. My life is just very hard right now. Close enough. So domain's all real numbers. Now the range, now look here, it's actually above the x-axis, which is going to mean your range is y greater than 0. It's either going to be greater than 0 or less than 0. You got a 50-50 shot. All right, and your asymptote here, as always, y equals 0. It is the x-axis. Okay. So that's if I give you the graph. So now I'm going to give you the equation. So in this case, I kind of give you different components of the attributes, but now you want to fill in the table. All right, so luckily for you, we have a handy dandy little calculator that will do this for us. All right, so if I want to plug it in and find the table values, menu, go over to table, delete the garbage. So for parentheses, that's not parentheses. For parentheses, fraction, then 1/4, that's not, nope, 1/2, parentheses, caret, x. All right, so I press enter, and we want the table value. So I want F6, and I do not want that. All right, so I went from -2 to +2. So at -2, you're going to fill in 16. And then the next one is 8, and then 4, then 2, and then 1. So those are going to be your table values. So you can do this literally on the calculator. If you want to do it by hand, by all means, you're more than welcome to. I am struggling so much. I chose the wrong one. I am projecting next door. Everything's fine. Hello. There we go. Okay, so just for frame of reference, right here, 0,4, this is your initial value. So when I say initial value, this is also the y-intercept, and it's your a value. The a value in your equation. Now, if you want to find the b value from your table, that's your common ratio. So you just have to look at your table and see, how do I get to the next value? So to go from, say, 2 to 1, if I'm multiplying, I have to multiply by 1/2. So this is your b value, which is your common ratio. So this idea right here is going to come in handy when we do the next one. All right, so notice how the numbers are getting smaller. Because the numbers are getting smaller, that is going to imply it is a decay. So your initial value, which is your A value, we said is 4. It's also in your equation. Your common ratio, which is your B value. Actually, let's do this. A equals 4. There we go. Then your B value, which is your common ratio, which is 1/2 from the equation. And now you actually need to find f of -3 and f of +3. You have options. You can do the table in your calculator. You can actually solve it using run matrix in the calculator. You can plug it in. Or your third option is you could actually use the table and just do it by hand. It's really up to you. I will say if the multiplier is not too bad, I would actually recommend doing this. So if I need f of -3, so that means I need to do the opposite. So I'm going to multiply by 2, which gives me 32. So I know f of -3 is 32. All right, and then if I want to go to 3, that means I need to multiply by 1/2 again. So half of 1 is just 1/2. Okay. All right, so now I'm going to go ahead and show you in the calculator. I'll go ahead and show you both ways. All right, so this is the table that we have. If I want to go down, it's 0.5, which is 1/2. And if you want to go to -3, there's 32 right there for you. And then if you want to do the run matrix way, goodbye garbage. Oh, goodbye garbage. There we go. So if I do 4 parentheses, 1/2 parentheses caret, then you can actually do -3, which gives you 32. And then if you want to find +3, you can just delete the negative, and there's 1/2. So it's really up to you which method you want to do. It all gives you the same thing. Do whatever you're most comfortable with. Okay. All right, so back to the show. At least I want to try to. Technology is hard. All right. All right. Now for the domain, your domain is going to be all real numbers, as always. Close enough. And your range, now because your values they're getting smaller, but they're still positive, which means it's above the x-axis, which means your range is going to be y greater than 0. And your asymptote, as always, y equals 0. All right, now onto the table for this third one over here. All right, so I will say the decimals, unless they're terminating nice decimals like 0.25 or 0.5, 0.625, unless they're terminating decimals, those decimals are going to be kind of dead information to you. It's kind of useless. So I would recommend looking at the whole numbers here at the bottom. All right, so we know your A value is 0, whatever that number is. So we know A is equal to 7. And then to go from 7 to 21, you're going to have to multiply times 3, which means your B value is equal to 3. All right, and because the numbers are getting bigger, that also implies we're going to have a growth. All right, so we know we have an initial value of 7. A equals 7. Then we have a common ratio of 3. So I'm going to use that information to write my equation. So y equals 7 parentheses 3 raised to the x. And now I want to find f of 3. So I'm just going to do this off to the side. Just going to plug it in run matrix. So when you plug it in, you're going to have 7 parentheses 3 raised to the 3rd power. And that's going to give you 189. So another option you have up here is because it ends at 2, you could just multiply by 3 again. So 63 times 3, which gives you 189. So if you want to just keep the pattern going from the table, you can. That's the pattern I actually recommend doing to find those values. However, if I tell you to find, say, f of 25, a table like that may not be as useful. All right, domain, as always, all real numbers. Oh my God. All right, range. So all my numbers are positive, which means it's above the x-axis, which means my range is greater than 0. And my asymptote, as always, y equals 0.